Hello, my name is Russ Whitehead, and I've been with LexisNexis for about 13 years working on the platform team, most recently working on security. I'm here today to talk to you about some of the security initiatives that we've been working on as we migrate the platform from the data center into the cloud. One of the first things that we felt was important to address was the management of secrets. Now, a secret is something like server credentials, encryption ciphers and passwords, so-called gateway credentials, things like that, that currently we're exposing those in ECL code, configuration files, and not a secure manner when you move out of a siloed data center. So Tony Fishbeck took the lead on this and architected and implemented a solution for secrets using industry third-party open source tools that lended themselves to both HPCC systems and to the cloud solution. The first of these is what we call Kubernetes secrets. Now, Kubernetes provides a command line interface for you to create key value stores of what will be secured as what we call secrets. You can give them a name and reference them in your code. When you install the platform, they get mounted on the pods on the Linux file system, and we access them on demand. They are not really centrally managed, but they can be dynamically updated periodically if a password changes or a URL changes or something like that. And we also cache them for performance, and it's configurable how long. So that's the Kubernetes secret. A broader and more secure method uses the HashiCorp Vault secret. A HashiCorp Vault is centrally located, and HPCC will access it via a URL. The same thing, you create a secret, a named secret with some key values that could be username, password, a URL, so forth. And again, these things are loaded dynamically on demand, but it's transparent to the caller which mechanism you use in the background and how they're accessed and inserted into the code. So I wanted to give you some examples of for ECL users. We use these internally for our configuration, authentication server, credentials, and so forth, but we also expose them for ECL developers. And what you see here is a couple examples, one using HTTP call, and you'll see that instead of embedding credentials in the HTTP call, we've referenced a named secret, MyCorp Connect. It's preceded by the keyword secret, and that tells the compiler to insert code to resolve that secret using Kubernetes. The second one, so-called, it's similar, but it includes a vault name, and that's how the compiler knows that this one is to be resolved using the HashiCorp Vault. And as I said, transparent to the ECL code, it just goes out, gets those values and inserts them and uses it, but in a much more secure manner. So the secret itself, like I said, is a collection of one or more key values in each named secret. So here's an example of a secret that contains a so-called information. As you can see, it's the gateway that you're trying to access, the username and password. You can put any kind of key values in your secrets, but of course the consumer of the secret dictates that you have, at least what it needs, username, password. You could add other things you wanted, like a secret owner or an expiration or something like that, but you have to have the things that we have here. So with secrets, you guys can start thinking about moving anything that you consider proprietary or secret out from your code and into a secrets repository. The next thing I want to talk about is Active Directory. And security managers in general. The platform supports multiple levels of security, which are configurable at installation time. Of course, you could have no security, which would be appropriate if, let's say, you have a laptop and you're just running our tutorial, or you have some simple data that's not really proprietary or anything like that. A lot of people use that just for standalone, testing our system out. The next level we have is what's called HT password. This utilizes a Linux flat password file that HPCC uses to authenticate you strictly by username and password. Once you have been authenticated, then the system's wide open and you have full access to all of the features and functions of the center. It's great for classroom environment or maybe departmental, where you have a small trusted set of users and you're not concerned about who's doing what. But the most robust one is the one that you're all familiar with. It's our Active Directory, or as it's often called, LDAP, Security Manager. This uses an external directory, is what it's called. We use Microsoft Active Directory to do basic password authentication, which, as you know, takes your username and password and verifies that you are the user that you claim to be. Once authenticated, we also have the ability to grant and deny access to features, ESP features and other features such as ECL watch, or spraying a file, or deleting metadata. Certain people, or we can put you in groups of people we can grant permissions to allow or deny that behavior. The other thing, which I'm sure you're all familiar with, is the ability to group your files and work units into scopes, and then we can grant and deny access to various scopes based on your username or group membership. So the first thing we did to migrate to the cloud was we just migrated the Active Directory as it currently works. We had to convert the way that it's configured. The old way uses what we call the configuration manager, which created an XML file with all the parameters. But the cloud way is to do what we call Helm charts. Those are YAML files that describe the configuration. So we just had to twist things around to make that work. And now we're forcing people to use secrets to specify the credentials used to access the Active Directory as an administrator, to do directory searches, modifications, and so forth. We tested this with both regular Active Directory and Azure Active Directory. We actually replicated our what we call our SDS Active Directory. That's the one you guys use every day. We migrated that to Azure, and we had to make some platform changes and a few other things, but we got it working and it works great. And it's not the best solution long-term, but it gives us a functional alternative to nothing. We also worked with the operations team to come up with a better hierarchy. Over the years, the structure of the directory is gotten kind of messy, big and wide, and it slows the searches down. So we've just come up with a better way going forward as we create new deployments to do this in a more efficient manner. And one of the biggest efforts was an initiative that Flavio started back in, I'm going to say December or January. He found this tool called Ping Castle that will analyze your use of Active Directory, and it comes up with a report with all kinds of security violations and warnings and caveats and things that you need to change. So we spent a lot of time, really up until just now, modifying the platform, modifying the way operations uses the Active Directory and so forth, to become compliant with Ping Castle. And I'm happy to report that Flavio is happy, at least for now, that we have come into compliance and it's much more secure. But LDAP is an old protocol. It's ancient. It was invented by the telephone companies way back then. It's not flexible. The new way is using a thing called open authentication, or Oauth. There's multiple versions of it. There were some security flaws in the first one, so they've come out with Oauth 2.0. We're going to be implementing an Oauth 2.0 security manager. So what is OAuth? It's an industry standard protocol for third-party authentication. And that means that we don't do the authentication ourselves. We delegate that to a third party, which could be our risk server or the Microsoft credentials or Google. I'm sure you guys have used it already when you log into Facebook or YouTube and it asks you for your Google credentials. That's using OAuth and a delegated third-party authentication. And what's important to note about this is that it uses tokens. Instead of, you pass the credentials to the authentication server one time, and it creates for you an authentication token. And for the rest of your session, you pass around this authentication token instead of credentials. Now, everybody within this trusted little network shares the same public and private encryption keys, and that's how you verify these tokens. Instead of having to call out and authenticate every time like we do with LDAP, it just uses, verifies the signature using your name and some other stuff and the token, and knows that you are who you say you are. So with the authentication token, then you can then request authorization to various resources that we talked about earlier, ECL watch, features like spraying a file or accessing a file scope. And like I said, it's all based on sharing public and private keys. That's how we authenticate without having to call out, and should speed things up. So I'm going to talk for a minute about authentication and the difference between LDAP, the current solution, and what we're hoping to get to with Oauth 2. Right now, when you authenticate, it calls out to our, what we call the SDS Active Directory server. That's just something that LexisNexis SDS, other people who use it will have their own Active Directory servers. But key here is that the username and password is sent pretty much with every request. And although the ESP will cache whether you're logged in or not, we have multiple ESPs behind a load balancer, so it could authenticate time and time again. So that's not real efficient. And the fact that we keep passwords around is not a real secure solution. So this is something that we hope to solve with OAuth 2.0. As I said, with the OAuth Security Manager, you will only authenticate once, get an authentication token, and pass that around for everything else you do subsequently. No more passing passwords around, no more keeping them in memory. And as I pointed out before, they'll get verified locally using public and private key encryption and digital signatures. Should be much faster. Now that's authentication. Now authorization is the next step. You've been authenticated, but can you access this feature or that feature or various functions on the platform? So the way we do it now with LDAP is, again, we send whatever the request is, we send your password and whatever the feature is that you want to access. And it calls out to LDAP and says, is this user who he says he is? Are they a member of this group? Can they access the resource? And it does this over and over. Again, we do cache, but as you load balance between different ESPs, it may have to do it over and over, and it can be costly. But with Oauth 2.0, as I said, you only authenticate once, and what you do is you request from whatever service it is you want to access, like let's just say file spray, you request permission to do that, and it will grant you an authentication and an authorization token. You then use that token for subsequent requests to access the resource. There's no more calling out to the authentication server. You just pass the tokens, they get verified, and again, that should speed things up greatly. So I'm going to show you real quick how the interface between a client and the authentication servers works once you've been authenticated. But there's a couple phrases that you're going to hear over and over if you're in this world. And I'll just go those real quick. The client is the application making a request. That would be your Thor or Roxy, let's say, trying to access a file. So the client will call the resource owner requesting permission to access whatever the resource is. That resource owner could be an ESP service, WS Access, WS Account, and so forth. The resource server is the actual server that hosts those resources, which would be the ESP web server process, ECL, Dolly, what have you. And finally, the authorization server is the server that actually grants the tokens. Once the resource owner says it's okay for you to access the resource, then you get an authorization server request to get a token. So this shows once you've already been authenticated, this is the sequence that you go through when you want to access, let's say, spray a file. The first step is the client, let's say ECL Watch, calls the resource owner and says, I'm this user identified by a token, and this is the resource I want to access. If it determines you're allowed, then it gives you an authorization grant, which is a token as well. The client then sends that token to the authorization server, which creates the real access token, which has expiration time in it and can carry a payload. Anything we want to put in it, we can. I won't get into that. But then using that token, the client can then access the resource server to do whatever it is, whether it's reading a file or spraying a file, whatever. It doesn't have to keep going out to the authorization server or resource owner. It just uses that token and just calls again and again to the resource server. That's going to help greatly, because right now what we do is we call out to LDAP. And I don't want to say every time, but it can be a lot. So with the new security manager, OAuth, what's going to be different? As I said, it's a third-party authenticator, so it's not going to be your familiar ECL Watch login screen. It's configurable who will do the authentication. I'm guessing we'll use someone like Risk, or maybe your Windows login, which uses Risk. But it could be Google, it could be Microsoft, it could be whatever. So it'll be that party's interface to log in. Because of that, we'll for free get the ability to do single sign-on, which lets you sign on once and then access multiple apps within the same domain. Multi-factor authentication, we all know about that, texting a code to your phone or whatever. And as I said, passwords will no longer be cached and exchanged. It's all token-based. And that's the whole key is take away from this, is that it's token-based. Things are going to be faster because you only have to request the token once. And these tokens are, it's probably, I won't say impossible, but they can't really be hijacked and reused. So it's going to be much, much, much more secure. So those are some of the things that we've done. Mark Kelly's going to talk about some of the internal things we've done, but you know, we've come a long way. We're not there yet. As you know, security is a journey, not a destination.
Hi. Version 8.2 of HPCC Systems contains some important security enhancements. This part of the presentation focuses on the new communication-based security changes. HPCC Systems has many different parts or programs that make up the whole. These include Thor, HTHOR, Dolly, Sasha, Roxy, ESP, ECL-CC Server, DFU Server, and some others. Most of the programs communicate with each other through the common interfaces of TCP and sockets. Browser to ESP traffic and some other communication paths can also use HTTP or HTTPS. Thor communicates heavily within its own universe between its manager and all its potentially hundreds of workers on many machines. And Roxy communicates heavily with its own other parts on potentially hundreds of machines. Roxy has server threads and agent threads on different nodes, and these use UDP, the User Datagram Protocol. UDP is used instead of TCP and Roxy due to its lower latency. But the lower latency gains also bring with it the added complexity of handling packet drops and retransmits and encryption. This is not a complete picture of all HPC systems communications paths, but it should illustrate the larger and common parts. Thor has its manager and all its workers. Roxy has its servers and agents. Most every component communicates with DALI at some point, and there is the user IDE and browser parts, which interact mostly with ESP. So I can show these communication paths. In almost all kinds of applications, encryption in transit is now expected and required, especially in the cloud, where your data is no longer residing within your physical data center, and your applications run in ephemeral VMs or containers, potentially shared on the same hardware with other unknown cloud users. Transport layer security, which everyone knows as TLS, is an industry standard and is now used for almost all TCP socket communication in HPCC Systems version 8.2. As mentioned earlier, Roxy uses UDP internally, and that is also now encrypted in version 8.2. Roxy encrypts all data packet payloads sent between its servers and agents with an AES block cipher. TLS needs a certificate and a key, and a crucial piece of all this is how HPCC Systems uses cert-manager together with Kubernetes in the cloud to create and manage and verify the numerous different certificates and keys used in an HPCC installation. For more information and a step-by-step tutorial of how to install cert-manager and configure HPCC Systems in the cloud to use cert-manager, please see the README file in the HPCC Systems GitHub repo Helm directory. cert-manager can also be configured to use HashiCorp Vault's PKI secrets engine, if desired. Information on using the Vault within cert-manager is also located in a separate README file in the HPCC Systems GitHub repo, and with the link shown in this slide. So basically, the steps to using HPCC systems in the cloud with encryption in transit are to 1. Configure your AKS cluster. 2. Install and configure cert-manager for your AKS cluster based on the tutorial and information mentioned above. 3. Install HPCC systems for your AKS cluster, specifying to use encryption in transit with the certificates.enabled property set to true. This can be done via a custom values.yaml file or on the Helm install command line. Once HPCC Systems is up and all the required pods are running, encryption in transit is then automatically enabled. ECL SOAP call can also then use a local certificate to access HPCC internal services. Simply add the mtls : tag to the service URL as shown in the slide. TLS connection time is slow as compared to unencrypted or traditional socket connections, primarily due to the handshake and key exchange. Saving and reusing a TLS session where possible for future connections can really improve connection time, since the handshake is essentially eliminated. And keep alive, where applicable, can be used to maintain the connection. But once connected, a symmetric key is used and the encryption and decryption is quite fast. A typical performance penalty might be around 10% or less. We are still testing to know more. I will also just mention a common cloud alternative to use TLS is the Istio service mesh. It is available in Kubernetes as a sidecar to encrypt and decrypt all traffic into and out of each Kubernetes pod, but it would still not cover Roxy UDP. There are also ways to encapsulate UDP within TCP, but we don't think that maintains the low latency UDP advantage. There are still a few things left to do. WS-ECL traffic from ESP to Roxy needs to be secured. Roxy cert and key management can be improved to use cert-manager similarly to how it is used elsewhere in HPCC systems. These tasks are currently being worked on for the 8.4 HPCC Systems release. Clients could also verify their certificate with a certificate authority in more places. And we could use TLS sessions in some places to improve connection time. And we continue to benchmark and tune message sizes and polling methods for better performance. That's it. Thank you.